So, welcome back to lectures on engineering mathematics 2. This is lecture number 10 on divergence theorem. So, in this lecture we will be talking about the divergence theorem, and that is basically the volume, how to get this from volume integrals to the surface integrals. So, that connection we will see in this lecture. So, just to recall that we have already discussed Green's theorem. So, the idea was that if we have a closed curve here in 2 dimensions, then we can interchange here this closed the integral over this closed curve to the area integral, which is done over this region which is covered by the curve C. So, this was the Green's theorem, and we sometimes call this Green's theorem in a plane, because we are talking about these 2 dimensions. And just to recall that this Green's theorem can be also written in this form. So, we can put this D or we can put there R. So, this R or D is the region covered by this curve C. So, this can be written in terms of this curl of this vector field F. So, again this curve integral or the line integral is equal to this curl and dot product with K, and this integral has to be done over the region bounded by or enclosed by this curve C. So, with this form of the Green's conclusion, we were able to extend it for 3 dimensions, where the curve can be in a 3 dimension space, and then this R, which was the region in the plane, will become a surface. So, that is what we have seen, its generalization in space, this curve integral. So, now the C is in space, and this the area or the area bounded by this curve, which is a surface. Now, we can do the surface integral, and this n was the normal to the surface. So, this was the Stokes theorem, which we have already discussed in the last lecture. Now, what we will do, that this is one form of writing this Green's theorem, where this extension was possible, this generalization was trivial to observe. What we will do now, there is another form which we can again rewrite this Green's theorem. Instead of this curl, we will use now the divergence, and from that form which will be written in the divergence, we can again extend to another result, which is called as the divergence theorem. So, there the extension will be again to 3 dimensions, but the extension, the type would be different, because here the extension was to 3 dimension, but the curve was a curve again in 3D, and that area which was in 2D in this case was a surface. Now, the extension which we are talking about in this lecture will be that this curve integral will become a surface integral in 3 dimensions, and then this region which was the surface in this Stokes theorem will become a volume integral. So, that is another generalization or the extension of the Green's theorem, which we will study today, which is the so called the divergence theorem. So, let us discuss the divergence theorem. So, we have this again, I have written this Green's theorem once again. So, we define here the vector field F in such a way that we have these 2 components F2 and minus F1. So, the minus sign is taken just to get actually the desired form of the Green's theorem, but we can actually work with like F1i and F2j as a standard notation. But here, just to show exactly that we are getting this form which we have written in this slide. So, we will take this vector field, the 2 dimensional again. So, F2xy, the first component, and the second component we have taken this minus F1xy. Having this, if we compute this divergence of this F. So, what will happen, the partial derivative of F2 and the minus the partial derivative of F1 with respect to y will come as a result of this divergence. So, which is precisely the integrand of this area integral, and that is the reason we have chosen this kind of form for this vector field f. So, if we know already all these knowledge we have gained in previous lecture, that the differential element along the tangent, that means basically the dr we are talking about, the derivative of r. So, that is dx and dyj we can write down, because r is usually xi plus yj. So, from here we can write dr, the differential element on the tangent is as dxi, and the second component is dy. So, having this, if we divide by its length, so the length of this dr or the magnitude. So, we have like dx square plus this dy square. So, we can write down this dr as dx square plus this dy square, and if we divide this by this factor, which is also we have defined earlier, we can call it as ds. So, ds is the incremental element on, or the differential element on the arc. So, if we divide by this factor ds to dr and dx and dy, so what we will get, this is going to be the unit tangent vector, because this is along the tangent and we have divided by its magnitude. So, now the magnitude of this dr over ds will be 1. So, that is the tangent, the unit tangent vector we are calling it, and we have dx over ds, and then we have dy over ds, because we have divided the whole equation by ds here and then here and then here. So, this dr over ds is the unit tangent vector, here we are denoting just by this t hat. And now, so this is the unit normal vector to C we are going to get out of this tangent vector. So, the unit, this normal vector will be the perpendicular to this tangent vector, which is written here dx over ds and dy over ds. So, we can just swap this, that is a trick, and put a minus sign there. So, this is normal, because we can just check here the t dot n, the dot product of the two will be exactly 0, because we have a dx over ds from there and then dy over ds from this n, and then we have minus sign. So, dy over ds and dx over ds. So, this gets cancelled because they both are the same. So, we get this 0. So, they two are perpendicular. So, this is tangent and this is normal, and since its magnitude is also 1. So, we have precisely this normal vector to this C at a point x y, at a general point, and then we can write this f1 dx plus f2 dy, the left hand side, the integrand of this left hand side in this Green's theorem, as f1 dx ds f2 dy ds. So, ds ds, and then we have here ds to compensate this differential element. And now, we can observe that this f1 dx over ds plus this f2 dy over ds can be written as the dot product with the normal vector. So, f was this f2 minus f1, and if we do this dot product with this n here, so we will get f2 with f2 we will have dy over ds, which is given here, and then with minus minus will be again plus, because there are two minus here. So, f1 will be with dx over ds. So, this is precisely f dot product with this normal vector to C, and then we have this ds vector. So, this f1 dx plus f2 dy is f dot n and this ds. So, the Green's theorem now we can write down or rewrite it again. So, this closed interval over this curve C, the closed curve C, the f1 dx and f2 dy is now f dot n ds, and so again going back here. So, equal to the right hand side, which was this area integral, partial derivative f2 with respect to x minus partial derivative f1 with respect to y, was the divergence of f. So, here this integrand we have replaced with the divergence of f. So, what we have now this result, which is a Green's theorem again, but just a way of writing, like earlier we have done in terms of the curl. Now, we have done this in terms of the divergence, and then this normal vector has come into the picture. So, the curve integral of this f dot n ds is equal to the area integral of the divergence of f and over the enclosed region by the C. So, now moving further from this result, we will come to the point of this generalization of the Green's theorem, which is the so called the divergence theorem. So, we have just observed that we have the Green's theorem, which can be written in this format, and if we replace. So, now we are going for the generalization without proof. So, this is just one way of understanding this. The formal proof is pretty lengthy. So, what we can do, we can replace this closed curve here for the generalization. The curve will be replaced by a surface. So, we are exactly going into the 3 dimensions from the 1 dimension, from the 2 dimensions. So, in the 2 dimension we have the curve now, and now we are talking about a surface. So, a closed surface S will be replaced in 3 dimension. Now, again the closed surface. So, the surface is closed now, and we will replace this bounding domain. So, there is a closed surface, that means there is a bounded area or the bounded region in 3 dimension. So, that is the bounding volume we are mentioning here. So, this bounding domain D will be replaced by this bounding volume which is M, and the vector field which was in 2 dimensions for the Green's theorem, we will now extend to the 3 dimensions. So, having just these 3 consideration, that this curve will be replaced by the surface, the bounding domain will be replaced by the volume, and the vector field which was in 2 dimensions will be replaced for 3 dimensions in 3 dimensions. So, what we have as a result, we have f dot n d sigma. So, again this curve integral is replaced by the surface integral, which is again over the closed surface, and then we have f dot n d sigma. So, the integrand is f dot n, here also we have f dot n. So, this n is again the unit normal to the surface, which is here outward unit normal. And then the right hand side, again we have a divergence, which is the same integrand. So, divergence of f, but now we are integrating over the volume, over the whole region enclosed by the surface S. So, just to conclude again, what is the divergence theorem? The flux of a vector field f1, f2, f3, the 3 components across a closed oriented surface. So, these terms we have already discussed before. So, we have a closed surface and it is oriented. So, we have the normal, which is defined in 2 dimensions normally. That means, we have the 2 surfaces which are distinguishable, and in the direction of the surface outward unit normal n. So, we have the outward unit normal on this surface. This is equal to the integral of, so the flux means the f dot n. If we integrate the f dot n over the surface, that is equal to the divergence of S over the region M, which is enclosed by the surface. So, I think the idea is clear. So, we have a region which is bounded by this surface here S, and we have the outward normal, the unit normal vector n to the surface, and we are denoting the enclosed region, which is the mass or the volume now. And then we have this result, which we have just discussed previously, as an extension of the Green's theorem, that the surface integral of this f dot n. So, this is precisely the component of this f in the direction of the unit normal, and we are integrating over the surface, which is equal to integrating the divergence of f on this volume, which is covered by the surface, the closed surface S. So, intuitively it states that sum of all sources minus the sum of all sinks. This is what the divergence, we have already seen this physical interpretation of the divergence. It is a tendency of the expansion or the compression. So, all these we are now integrating over the whole region, and that is just equal to the net flow out of the region. So, we are just integrating over the surface at one end and the normal component of this flux. So, these two integrals are equal. So, that is an interesting result which we will use in now or apply for solving several problems, because we will observe that in most of the cases which I have demonstrated here in this lecture, or I will demonstrate now. So, this integral, the region integral is this volume integral is pretty easy as compared to the surface integral. So, in some problems we will verify the divergence theorem, that means that both the integrals we will evaluate, and in some problems we will observe that this is quite complicated, having this flux over the surface, but through this area, through this volume integral, we can easily compute this flux. Okay, so, coming to the example problem here, we will verify in this the divergence theorem for this field, which is x I, y j and z k. So, the three components over the sphere whose radius is 9. So, we have the surface, we have the flux, and then we will verify the divergence theorem. So, for that we need to get the unit normal vector, because we need to compute f dot n. So, unit normal vector on this sphere can easily be computed if we just get the gradient of this f. So, this is gradient of first this f is the given surface. So, if we compute this gradient, we have 2 x with the ith component, then we have 2 y the jth, and then 2 z multiplied by this unit vector k. And to have the normal, so the unit normal we have to also divide by the magnitude of this one. So, 4 y square and then 4 z square. So, this 2 can go out, and that will cancel out from the numerator. So, we have then the x I, then we have y j, then we have z k, these unit vectors, and then we have this 2 is already settled. So, we have x square plus y square plus z square, that is 9. So, which is 3 here. So, this is what we have written, the unit normal vector is x I, y j and plus z k divided by 3. So, now the f dot n we can compute because we need in the surface integral. So, f dot n. So, f is given x I, y j, z k, and the dot product with this n will give 1 by 3, then we have here x square, then we have y square, then we have here the z square. So, this is x square, y square and plus z square, and which is 3 on this surface on this sphere, because on the surface x square plus y square z is 9, because in the surface integral we will be integrating this f dot n over the surface. So, this f dot n is 3. So, because this x square plus y square plus z square is 9 there, and 9 divided by 3 is 3. So, this f dot n d sigma, the surface integral we will evaluate now. We know this f dot n is 3. So, it is very simple now. So, 3 and this surface integral. So, 3 and just the surface integral with just 1 as its integrand. So, that is just the surface area of the given surface, and we know the surface area of the sphere. So, we have 3 times and 4 pi r square, r is 3, the radius of the sphere is 3. So, we got this 108 pi, this surface integral. The second we will evaluate that volume integral. So, for that we need to get the divergence of f. So, for the divergence of f, we have partial derivative with respect to x of the first component, which is x, partial derivative of y, the second component of f, partial derivative of z, and the third component of f, which is z. So, this is 1 here, and again here also 1, and at this place also we have 1. So, this is simply 3, the divergence of f. And now we can compute the other side integral of this divergence theorem, which is the divergence f integrated over the volume V, or we have written d here. So, this is exactly the 3 times this integral over the volume V. So, 3 is again the constant, and this integral, the triple integral, will give the volume of the sphere, which is 4 by 3 pi and this r cube, and again if we see this is coming to be 108 pi. So, these two values are same. So, this is the verification we have done for the divergence theorem. We will consider some more problems to practice now. So, here the question is find the flux where we have component x y, y z and x z outward through the surface, that means f dot n we are talking about, and the surface is given the cube in the first octant, which is bounded by these planes x is equal to 2, y is equal to 2 and z is equal to 2. So, coming back to the divergence of f, the divergence of f will be, because you have x y and y z and then we have x z, the 3 component. So, here the partial derivative of this x y with respect to x will give y here, the partial derivative with respect to z, y will get z here, and here partial derivative with respect to z. So, we will get x here. So, the flux we can get with this f dot n integrated over this surface, and that is given by. So, we are not, I am not usually using this arrow sign on this gradient operator. So, here the integral over this volume, which is bounded by this cube. So, the divergence f we have computed here, that is x plus y plus z. So, using this divergence theorem, this flux we are computing using this volume integral. So, that is in our case it is a cube which is lying in the first octant. So, that means the x is varying from 0 to 2, y is also varying from 0 to 2 and z is also varying from 0 to 2. So, we have these limits for this is the integrand and then dx dy dz. So, we have eventually 3 integrals here, one is over x, then y on z, and all 3 will give the same value. So, the first one if we compute, we will get like x square by 2, then the limit 0 to 2, and there are 2 more integrals sitting there 0 to 2 and 0 to 2. So, this is for just for x. Similarly, for y and z we will get. So, this is the value coming as 2 there, and if we integrate, then this one with respect to y we will get another 2 and then we will get 2. So, we have the 8 and then there are 3. So, we will get then 24 as a result of this whole integral. So, here we have not verified, but we have just used the convenience of this divergence theorem to evaluate this flux using the volume integral. If we would have computed this flux using this surface integral, then we have these 6 phases, and for each we have to evaluate this f dot n and then sum it up. Naturally, we will get 24, but it seems that this is much easier now with this volume integral. So, that is one of the applications of this divergence theorem with this conversion from the surface integral to the volume integral actually works. So, here we will see that if V is the volume enclosed by a closed surface S, and this f is given by 3 times x, 2 times y and z times this k, then we will show that this flux integral f dot n ds is nothing but 6 times the volume of this surface. So, here we will compute, naturally we will apply the divergence theorem to see that how this 6 times v is coming, and the idea is exactly from here. So, the divergence of this 3 x 2 y and z is nothing but 3 plus 2 plus 1. So, that is 6 here, and if we apply the divergence theorem now. So, the Gauss divergence theorem says that f dot n over the sigma which is just 6 here. So, 6 and this volume integral, which is the volume of the surface enclosed by this surface S. So, we will get 6 times the volume. So, this flux integral is nothing but the 6 times the volume. So, very simple example here to see the importance of this divergence theorem again. So, the next problem we will evaluate this integral. So, this is a surface integral if you look at. So, we have some kind of f here, then we have f dot n d sigma. So, this is exactly the flux we are talking about in divergence theorem, and this S is the surface of the cube again. It is bounded by this up to x is equal to 3, y from 0 to 3 and z is 0 to 3. So, it is similar to one of the problems we have just done. So, the f dot n this d sigma. So, again if we integrate this directly on S, this is going to be complicated. So, what we will do, we will use the divergence theorem. For that we need to get the divergence of this given vector field. So, what is the divergence? If we partial derivative of this component with respect to x, we will get 3 x square, and then partial derivative here with respect to y, we will get minus 2 x square, partial derivative with respect to z, that is 0 there. So, we have 2 x square or 3 x square minus 2 x square, and the value is just x square. So, this x square, the divergence, this x square is to be integrated over this cube. So, the divergence theorem says that this flux integral is nothing but this volume integral, where we have the divergence here, and this is x square. So, dx, dy and dz, we have to integrate this, which is a simple integration now, because the limits x, y, z both all three are going from 0 to 3, and we are just integrating x square. So, one can do this integration and we will get the value 83. So, again one more application where we have seen that this volume integral is very simple as compared to the surface integral, which you would have done with in all these phases. So, this is just the last example where we will be talking about that how to verify again this divergence theorem on this problem, where we have a cone. The surface is given as the cone z is equal to square root x square plus y square, and the cone goes up to where we have x square plus y square less than or equal to 1. So, this is the open surface, this cone. So, if we close it with this disk, so on the top we are closing it with this x square plus y square minus less than equal to 1 with this disk there at the z is equal to 1 plane. The f is given by x I, y j and z k. So, we have to verify this, that means this f dot n over the surface, and then the divergence f over this covered volume, which we are denoting here by m. So, we have z is equal to square root x square plus y square, one surface which is the cone there, and then the another surface we have the disk, which is the cap on this cone. So, this is the situation. This cone is denoted by the surface n, and its cover there we have denoted by S2. So, surface integral, if we compute first, that means we have two surfaces S1 and S2. So, this integral we have written in two integrals S1 and over S2, this f dot n. So, for S1 surface we need to compute the normal. So, the for normal we have the surface here z square is equal to this x square plus y square, and for the outer normal. So, let us take our f here like x square plus y square and minus z square. So, from here x square plus y square minus z square, we will compute the normal. So, the gradient, and it will be divided by its magnitude. So, on this surface, however, we have this x square plus y square is equal to z square. So, we can replace this by z square. So, we will get this expression for the unit normal. And then f dot n, if we compute, so what was the f? The f was x I plus this y j, and then we have this z k. So, if we compute this f dot n, so what will happen? We have this x square there, we have y square there, then we have minus z square, and then divided by this factor square root 2 z. But if you look at the numerator, we have x square plus y square and minus z square, and from the on the surface this is going to be 0, because our surface is z square is equal to x square plus y square. So, this dot product with this f is going to be 0. That means, this first integral, the first surface integral over this S 1 is going to be 0. So, f dot n d sigma over this S 1 we will be getting as 0. The second integral we will compute now. So, for the second integral, so this is our surface which is lying in this z is equal to 1 plane, and we know already without any calculation that what is the normal to this surface. So, this is plane z is equal to 1, and the normal will be just in the direction of this k. So, for S 2 the normal unit vector is the unit vector this k, and then f dot n we can compute, because the f is x I, y, j and z k. So, this is just simply z, and then f dot n d sigma we can compute as we discussed already that this is coming to be 0. The second term here we have the f dot n is z, and z is 1 on the surface. So, this z is 1 on S 2. So, having this, we have this 1 as an integrand, and we are integrating over this S 2. So, that is nothing but the area of this disk, which is pi r square, r is 1. So, we have the value pi there. Now, we will compute the other integral, which is over the volume, over the whole volume here given in this figure. So, volume integral we need to compute the divergence of f. So, the divergence of f if we compute now, so since f is given as here, so the divergence of f, partial derivative of x with respect to 1, here also 1, we will get 1. So, that is 3 there. So, this is 3, and the volume of this volume enclosed by this surface. So, that we know already is the cone, and we know the formula that the volume of the cone when we have height h and the radius r, that is pi r square, and this h by 3. So, here we can we have the radius 1, and the height is also 1 here. So, height is 1 and the radius is also 1. So, we can compute there 3 and pi r square and this 1 by 3. So, this value is coming to be pi, and here also the surface integral was also pi. So, we have verified the divergence theorem in this case, where the surface was a little bit more complicated. There were two surfaces, one was cone and the other one was this disk. Well, so this is these are the references we have used for preparing this lecture, and just to conclude that we have discussed the divergence theorem, which is very useful, and we have seen with the help of many examples, and it says that the surface integral or the flux across the surface in the direction of normal can be computed with the help of this divergence of f and integrated over the volume covered by this closed surface S. So, that is all for this lecture, and thank you very much for your attention.